Okay, so up until this point, we haven't actually developed a method for solving a kind of differential equation, but now we are. So in this section, which is titled Separable Equations, we're going to define and develop a technique for solving separable equations. Your natural question next should be, what is a separable equation? And so that's what we're going to focus on right now. That sound was me dropping my stylus. A differential equation, so we're talking about differential equations, and specifically a a first order differential equation is called separable if it has the form dy dx equals g of x times f of y. Okay, so this sounds weird, but this is the key piece of identifying what makes a separable equation. You can separate x terms from y terms using multiplication. So like they'll factor into different factors that are distinct from each other. So here let's do a few examples. Okay, identify whether the DE is separable. So, one, let's try xy times y prime equals x squared plus 1, okay? So our task here is to write this as an equation with y prime by itself on one side, and on the other side we want to be able to express a term involving only x's and a term involving only y separated by multiplication. So if I divide both sides by xy, okay, and here's the key insight. Notice that there's just a y in the denominator, and I can write this as x squared plus 1 over x times 1 over y. Okay, so this right here is our g of x, and this right here is our f of y, and they're separated by multiplication. Separable. Okay, that worked out. Let's try a different one. 2. How about du dt equals 1 plus t to the fourth all over ut squared plus u to the fourth t squared. Okay, so don't get too intimidated by the fact that we're using different letters now. Remember that all that matters is we're separating the right hand side of this equation into two terms, one involving only u, one involving only t. So notice then that we can factor out a t squared from the denominator. And so we can just write the t terms in their own factor, 1 plus t to the 4 over t squared times 1 over u plus u to the fourth. And there it is again. This is our g of t, and this is our f of u, okay? Separated by multiplication. It's separable. Lastly, let's try out this one. How about xy prime plus y equals x ln of x? So again, the strategy here, get y prime by itself. So xy prime equals x ln of x minus y. And then y prime equals, if we divide by x, right? X ln of x minus y over x. Here, though, we cannot separate y using multiplication. So the only thing we could conceivably do here is do ln of x minus y over x. And again, there's no way to factor out a y or an x here. That would leave this in a separable form. So this one is not separable. You're welcome to try, but it's not going to happen. So with all that said, how do we solve a separable equation? It's a valid question. And the important thing here that we're going to do first, right, is we're going to let h of y equals 1 over f of y. Here's y. No pun intended. So start with the dE, which is dy dx equals g of x times f of y. Because what we're actually going to end up doing is we're going to divide both sides by f of y. So we're going to have 1 over f of y times dy dx equals g of x. And if we just write this right here as h of y, it just makes it easier, okay? So let's just go ahead and do that now. Okay, so make the mental conversion in your head, write it down, and then we're going to forget that f of y was everything, okay? So far all we've done is we've rewritten this equation so that we have all the expressions of y on one side of the equation, all the expressions involving x on the right side of the equation. So at this point, what we can do is we can sort of multiply. I'm putting that in terms of quotation marks because we're not really to get the differential form. I am not going to get into the details of this, okay? But essentially what we're doing is we're just going to move the dx over to the other side of the equation. I want to be clear that you are not prepared to make any statements about this differential form as it is, okay? It's an equation of differential forms. This statement on its own is meaningless to us, okay? It's the next step that actually matters, okay? By theorem on antiderivatives, you know the one where if the derivatives are the same, the antiderivative should be the same, except for they possibly differ by a constant, right? Then the integral of h of y dy equals the integral of g of x dx. And these are indefinite integrals, right? So they could differ by a constant. So really, this is going to give us a capital H of y equals capital G of x plus c, where these are antiderivatives of little h and g respectively, okay? Now, if h is 1-to-1 and we're able to isolate y, great. If not, we would have to leave it like this, okay? So in some cases, it's just not going to work out nicely as a y explicitly given as a function of x. But this does give us, at least implicitly, a relation between y and x that is going to give us the solution curves to the system. So this is the solution. And I know it doesn't look like a solution, right? It's not like it's given in an explicit form, but we've come up with a method to try to solve the system, or the dE, I should say. All right, so let's see an example of using this technique, right? So we're going to solve y prime plus x e to the y equals 0. Okay, so first things first, let's isolate y prime. Y prime equals negative x e to the y. Is this separable? It is, because we have the x term, negative x, separated by a multiplication from the y term, which is e to the y. So if we go ahead and multiply both sides by e to the negative y, okay, dy dx equals negative x, and then we're going to get that differential form equation, which is, again, not anything meaningful to us, but it's just a way for us to get in the right format. And now we integrate. So integral of e to the negative y dy equals integral of negative x dx, which yields negative e to the negative y equals negative x squared over 2 plus c. In this case, we can isolate y, okay? It's just going to take a couple of quick steps. Be careful here, okay, in how you're solving this equation. Remember that you have the plus c at this point, okay? So things are going to happen to the c that you may not have wanted to happen otherwise, but they are going to happen. So multiply both sides by -1. So that's going to be a negative c now. Again, the actual value of c doesn't matter, but because we already had a c, we're going to have to do things to it. -y equals natural log of x squared over 2 minus c, applied to both of them at the same time. And then y equals negative natural log of x squared over 2 minus c. And that's your answer. That is it. That's the solution. And it's given explicitly as a function, which is pretty cool. Okay, let's do an example of an IVP now. Example. So we're going to solve y prime tangent of x equals 1 plus y, subject to y of pi over 3 equals 1 for x between 0 and pi over 2. We need that so that we can find a unique particular solution, and that's because tangent has is periodic. So depending on the value of x, we're not going to pinpoint an exact value. All right, so let's go ahead and solve the DE first, right, to get the family of solutions. Y prime equals 1 plus y over tangent of x, okay, which is the same as if we move all the y terms to the y prime side, we're going to have 1 over 1 plus y dy equals 1 over tangent x dx. So we have integral of dy over 1 plus y equals the integral of cotangent x dx. Okay, integral of cotangent x, we're given that using, it's basically a u substitution. At this point, you can memorize it and write it down in a formula card. So ln of absolute value 1 plus y equals ln of absolute value of sine of x plus c, okay? Now, sine of x for the range that we're specifically given is going to be always positive, so we don't need the absolute value bars there. We do have to keep a restriction on y just because we don't have any information about y necessarily right now. The other thing that we can do, though, is we can apply the initial condition. So initial condition going to be applied here. So y of pi over 3 equals 1 implies the ln of, in this case, 1 plus 1, which is 2, equals the ln of sine of pi over 3 plus c. Okay, so we end up with ln of 2 minus ln of sine of pi over 3 is root 3 over 2 equals c. Okay, and just for simplicity's sake, then we're going to combine these ln terms. Ln of 2 over root 3 over 2, which means c is actually ln of 4 over root 3. Okay, very nice. And so we do get a particular solution here. So I'm going to put it all together now. So ln of 1 plus y equals ln of sine of x plus ln of 4 root 3. Okay. One really cool thing here is that we can combine this into ln of 4 root 3 times sine of x. And these are both natural logs. So we can clear the ln's. We're actually going to get 1 plus y, absolute value, is equal to 4 over root 3 sine of x. Okay, and so then if you know that this how this is going to work out, right, we can split into two equations, which actually is not going to give us a function, right, anymore. So we could write it implicitly, right, as two functions. So we can have y1, sorry, let's go ahead and actually do the work here. So 1 plus y1 equals 4 root 3 sine of x, or 1 plus y2 equals negative 4 root 3 sine of x, and then isolate y1 and y2. Okay, so y1 is a shifted sine, which has an amplitude of 4 over root 3. y2 is almost that, but the sine curve is reflected about the y-axis. Even though it's, sorry, not about the y-axis, but about the axis of over which it oscillates, and then we just shift it down by 1. Okay, so you can either get an implicit solution or two explicit solutions. But notice now that each one, right, this defines a relation, and the two explicit solutions define two functions that satisfy this particular DE, which is a common thread. I mean, that happens a lot. You won't have to worry too much about finding explicit solutions all the time. This is just a way for us to be able to graph them, but you could also use your computer algebra system to graph the implicit solution as well.